right, everyone, let's get started. This is Nick Danielson from Symetrix, and today we'll be covering GPIO, also known as General Purpose Inputs and Outputs. We'll also cover some basic logic circuits you might need as you're implementing them in Composer as well. Just so you know, all of our DSPs, with the exception of the Prism 0x0, have GPIO on them. In this webinar, we are going to focus on the Composer-based stuff, Radius NX, Prism, Solus NX, and Edge, basically. As usual, please ask any questions as we go along. I'll get to them. Do note that this will be recorded as well, so you can always go back and re-up on it later as well. So, okay, let's jump in. So what is GPIO? Put simply, they're open inputs and outputs on the back of the DSP. They're used to interface with other electronic devices. The larger DSPs, such as the Radius NX and the Prism 16 that we have here, those all have 8 switch inputs, which are also switchable to 4 potentiometer inputs. That's all done in Composer software, that switching, and 8 logic outputs. DSPs with smaller I/O counts, like Prism 4x4 and the Solus NX 4x4, will have fewer GPIO as well. These ones have 4 switch inputs and 4 logic outputs. So it can vary a bit, but basically they all have some amount of GPIO. Probably the most common example of using the general purpose inputs, or external control inputs as they're known in our universe, really. One of the most common examples is triggering an emergency system mute based on fire alarm panel status. Another super common usage would be to use them as a volume control, where you have an RC3 or just a standard 10K pot wired in, and that would usually be driving an audio fader inside the DSP, or maybe driving a control fader that's got some scaling on it, that sort of thing. We'll look at that in Composer as well. And an example of using the logic outputs would be to directly drive an LED as a mute status indicator, or to trigger a power sequencer to fire up the system. So before we dive into Composer and worry about how to assign these things to faders and buttons, I do want to cover first what the GPIO looks like on the back of the DSP and how to wire things up correctly. So let's start with the external control inputs. Each of these control inputs can be individually configured in Composer, as I mentioned, to be used as either a dual switch input or as a potentiometer input. Each input has an A and a B and a shared ground between the two contacts, the A and the B. So for a single switch, just simply wire into either A or B, basically, and ground, pretty straightforward. If you have 2 switches, you can just simply wire into the other available contact, B in this case, and use that shared ground. Both switches will still function independently. And for using one of our RC3s or just the typical 10K linear pot as an analog control, you'll wire the pot into all 3 contacts. Of course, in pot mode, the A contact there has a 3.3 volt voltage reference, and B is the input coming from the wiper of the pot. Something to know, if you accidentally happen to wire the A and the B backwards, the pot will, of course, function backwards. You turn it up, and the volume's going to go down, and vice versa. You can correct for that in Composer software by calibrating the input without actually having to rewire anything. So we'll look at that in a few minutes as well. Let's take a quick look over the logic outputs. So each logic output is actually the open collector of a switching transistor. Whether you care about that detail or not, just know that when it's in its default non-activated state, the logic output is internally pulled high to 5 volts. So that's effectively like the resting position of the logic output. Even if you have no logic programming in your DSP happening, there's going to be 5 volts on these logic outputs, which you can use, by the way, to detect. You could detect that 5 volt presence from a different DSP to monitor the status. So that's a little trick, knowing that 5 volts is always there. Okay, so inactive state is 5 volts. When the logic output is activated via your DSP programming, that 5 volt is shunted to ground to the transistor's emitter, and that results in 0 volts at the logic output. So all that being said, these are not dry contacts or built-in relays for that matter. These, but it does make it possible to drive a relay having this voltage here. So we're basically active low is how you could think of these. And it is possible to invert these states. So if you could make it active high if you wanted to. That's all done in Composer, which we will look at later. I don't want to bore you to death with the specs of the logic outputs, but it is worth knowing so you have an idea of what you can drive with these things. As we already talked about, they're pulled high to 5 volts when they're inactive. And again, they go low to 0 volts when they're activated. The max current that we can source is 10 milliamps from the logic output. The max external power supply voltage is 24 volts. And the max external power supply current sinking is 50 milliamps. So that's the max you'd want to sink into the logic output. So all this stuff is in the Composer help file in the hardware pages, so you don't need to memorize this. Just be aware of these limits and that they're there. So let's have a real quick look at driving LEDs first. The simplest way to drive an LED is literally just to plug it in. It's really, as long as it's capable of being driven by 5 volts and 10 milliamps is enough current for this LED, then you're good to go. There's no series resistor needed in that case. Just obviously check the data sheet for your LED when in doubt. In the case of that MX395 that we briefly looked at earlier on the other slide, their LED is actually getting its power from the phantom power on the audio lines, so we actually don't have to worry about that. But pin 5 on their cable is looking for either 5 volts or 0 volts to toggle between the red and the green states, as you can kind of see in the lower left here. So we could simply directly connect to a couple of the pins on their cable, basically, and we're good to go to toggle between the red and green states. If you have a beefier LED, another option is to use an external power supply. So you'd hook that up as below. As long as that power supply, again, is a max of 24 volts, and you don't try to sink more than 50 milliamps into the logic output, this will totally be cool. That's it on LEDs. Let's look at relays a little bit. So you can drive relays, but of course, it all depends on the specs of the relay. Considering the logic output can source, 10 milliamps, driving a mechanical relay is probably not going to happen, directly. You'd want to use an external supply for that. Again, just make sure that the current getting sunk is less than 50 milliamps. So just keep an eye on the coil current of the relay that's a spec, and do include that flyback diode as well, just to knock out any voltage spikes when you turn off the coil. Without that, you run the risk of destroying the transistor inside the logic output. So always have that. Another good option for relays is a solid state relay. Those have an internal LED instead of a coil, so they have way lower turn on requirements. Again, look at the specs, but there are plenty out there that could be driven directly off the logic output. One more slide, I promise, and we'll hit Composer. If you happen to run out of GPIO on the back of a DSP, you can expand that system by using an xControl. This is basically just a PoE expander. It lives on the Ethernet network, the control network, along with the DSP, and that gives you an extra 8 potentiometer inputs or 16 switches or a mix thereof, as well as 16 extra logic outputs. So you can always expand your GPIO. Okay, so with all that in mind, let's just jump over to Composer and walk through a few scenarios with GPIO, and we'll be using some logic modules to make that happen. Okay, let me get out to site view here. So one of the first things that I would do in Composer, I've just got an NX 4x4 here on my desk. One of the first things I'd typically do is how you decide how you want to use your external control inputs. I know that we're going to use one switch and one potentiometer in this case. You may not know that ahead of time, and that's okay too, but I mentioned earlier you can switch between dual switch mode and potentiometer mode in the software. So let's just start by having a look at that. On site view, if you right-click your DSP, you can go to Configure External Control Inputs. And this shows the 2 control inputs we've got on this NX 4x4. So it's just simply switchable. I'm actually online right now, but you can switch these when you're offline to change between pot mode and dual switch closure mode. Let's go over to input number 2, because that's the one I actually have a potentiometer hooked into right now. So right here is where you can do some pot calibration. So you can check out right here. As I wiggle the knob, we see what we're coming in as. It goes from 0 to 100%, of course. Pots don't really have the best tolerance, so they may not actually reach their stated value. But there is something you can do about that. This one that I have here is just fine. It does the full range, no problem. But let's say you turn the pot all the way down and it never quite reaches 0%. What you can do is, let's say it goes down to 2%, as low as it goes. At that point, you can hit set minimum position, and that's going to now tell the software that where the true bottom of that pot is, regardless of its actual resistance. The same goes for the max. Maybe it only goes up to that or something. You can go set the max position here. And now the DSP is going to see a good clean 0 to 100%, regardless of what the pot resistance is. Okay. Now I mentioned earlier, if you should happen to wire your pot backwards, probably not going to happen very often, but sometimes things happen like that. You can fix that in here by turning the pot down and set that as your maximum position, which sounds super counterintuitive, but I mean, the pot's wired backwards, so you got to do it. Turn it down, hit set max position, do the same for the top of the pot, turn it up, and set that as the minimum position. And now at that point, you've calibrated the software to treat it as a correctly wired pot, basically. So that's how you would fix that in software. And let's reset that madness. And let's walk through building some logic circuits to work with this GPIO. All right, so we're going to start with external control inputs, and we're going to build one of the easiest and also one of the most commonly used things when it comes to GPIO, and that is we're just going to build an emergency system mute from scratch. And it has just a few elements in it. So let's go over to our toolkit. We're going to be just pulling a lot of stuff from the control modules area. That's where all the logic modules live. Control inputs. This is where we find all our buttons, our control buttons and control faders and whatnot. So let's grab in a one button momentary to start with. And if we double click this, this is our usual button GUI here. What we're going to do first is, just like anything in Composer, if you want to control it, you right click on it, right click directly on the object, and you hit set up to remote control. Pretty straightforward. I'm going to do that. Now what we do here is we choose local analog input. This is your GPIO, directly on the hardware itself. So we go down to select analog control and we hit switch 1A. That's where I have my switch wired, is in 1A. And I'm going to go to tools and turn on superimpose assigned remote control numbers. That way you guys can see what that looks like. We've actually assigned switch 1A to this button now, as you can see here. We're going to be taking advantage of, when you push the button down, that's what these faders tell you, what percentage, what logic level it's going to put out of the output right here. So we push the button down, it's putting out 100%. Release the button, it puts out 0%. So on or off, right? So what we want to do is use this button that we've now assigned to our switch. We want to use that to toggle between a couple of mute and unmute state for the system. So what we're going to do is take advantage of these existing presets that come with every Composer software, or every Composer file rather, that you make. They're in there by default. So Tools, Presets Manager, and you'll see that we've got a mute all and an unmute all hardware, 999 and 1000. So what we want to have happen is we want to, when this button gets pushed in, we want to fire our preset 999 to mute everything. And when the button is off, when the fire alarm is done doing its thing, it's going to pop our momentary button out. And we need that to automatically fire our preset 1000 to unmute all hardware. So what we're going to do is grab some preset trigger modules. And that's going to be found under Control Accessories. And I'm going to drag in a dual preset trigger since that's kind of a 2-for-1. It brings out 2 different preset trigger modules as a package. So I'm going to go ahead and wire this in. So when the button's hot, when it's logic high, it's going to fire this preset right here. And we're going to make that fire our preset 999, which is our mute preset. That's the easy part. The less maybe straightforward part is that when the button is off, you'll notice here when the button is off, it puts out 0%. That's not going to trigger anything because that's logic low. That's not going to trigger anything. So if we were to just split off of this, for instance, it's not going to do anything. It's only going to, there's going to be 2 presets fighting each other. What we need is for this preset to be fired when the button is off. So the way we do that is with an inverter module, which is going to be found over here in processes, I believe. So we put this guy in line and now split that off the button here. Now when this button is off, it's going to be putting out 0%. However, our inverter is going to flip that back to 100% right here, and that will now fire our unmute preset when this button is off. So that's pretty much it on building that guy from scratch. I'm going to go ahead and just actually push this file so we can see what it looks like. I have my switch wired in here. And let me pull up both these preset triggers as well as the inverter here so we can kind of see what's going on there. Right now, as you can see, the button is off. I'm going to hide this flag so we can see the button. So button's off. It's putting out 0%. Our inverter is flipping that to 100%. And we have our unmute preset, which I forgot to actually change to 1000. So our unmute preset is now being fired. I'm going to push the button that I have here. And you can see that our button is now hot. And our preset number 1 is getting fired. Our preset trigger 1 here is fired, triggering our preset 999 to mute the system, basically. If I release the button, our inverter is doing its work, flipping that 0% to 100%, and now we are unmuted. Okay. So I will say that you don't have to build that from scratch every time. We do have a super module that has all this built in already for you. I just wanted to show you how it works from scratch, but you can import this from tools. Let me just show you where that's at really quick. Import the super module over here and go to examples, tools, and you can find it in this. There's a whole pile in here of stuff that's included. Emergency system mute. It's just right here waiting for you to use. I've already got it pulled in, so we can just have a look here. All it has is just a little basic GUI with those same preset numbers that we just looked at. And there's the button. You would just simply right-click this button and set it up to remote control, as we just did with that other button. Same deal there. Okay, let's move on to another type of usage for our external control inputs. So another commonly one, just a mic push to talk. Pretty straightforward stuff. There's a couple ways to do this. I'm just going to pick one of them and show you in the interest of time. Again, we'll use another momentary button coming in from our control inputs. I do, by the way, have just a sine wave generator just to give us some sort of audio indication here, just something to look at a meter with. So I'm going to use the other side of this audio via here. That's the sine wave. We have something to monitor, and let's go up to mixers and gains. We're going to do the push to talk with a VCA. Again, it's just one way to skin the cat. As usual with Composer, there's a lot of ways to do things. But for a single mic channel, this is a pretty straightforward way to do it. We're going to wire this button into the control input of the VCA. And the audio will pass into the audio input of the VCA. And just for a little bit of level indication, I'm going to put an audio meter on the output of the VCA, just so we can kind of just see what happens here. And as usual, we need to assign control to the button. So this would be our mic push to talk button. We're going to right-click this guy here, set it up to remote control, and we'll choose switch 1A again. OK on that and do a quick push. Okay. Let's bring up our VCA and our audio meter here. So right now there's no audio, of course. When I push this button, it's going to drive the VCA to open, which is see the actual gain come up to 0 dB. So I'm now holding the physical button. Release it, it closes the VCA and audio stops. Very simple. Another way to do it would be to drive the a gain block instead of the VCA. I'll just show you that really quick here. So we are going to have time, I think. So here, let me just make a little space here. I'm going to use the same, well, actually just to avoid confusion, I'm going to just break this connection here. And we'll get, I'm going to split the audio off of this audio via here. And I'll duplicate this meter. Pop that down here. So what we normally do then, we've already got this button assigned to our physical button, our GPIO. So this only puts out a control signal output. There's no audio, of course, from this. Is just a button on or off. But we need to wait a way to drive the mute button this time on this gain block. And what's going to happen is that this thing is actually going to work in reverse from what we want. I'm going to show you that step first. So the first step is to get this mute button to be driven by our momentary button here, which is being controlled by our physical switch. So if we right-click this mute button, set up to remote control again, this time we choose a control signal assignment. This is like an internal control voltage. You could think of it as if you're a synthesizer nerd like me. Hit select, and we can choose from amongst all the possible logic modules that have, logic outputs or inputs on them. Outputs, rather. So we go to one button momentary 1121. See that number right there is a specific identifier for that module. So we want to find that one. And we go to button 1, hit OK on that. And now we have a CS. That means this mute button is now being driven by a control signal. Give it a quick push. And let's get the meter up. So right now, audio is passing. And we push the button, and the audio goes away, as it should. But the thing is we wanted to push to talk, and right now we have a push to mute, which is not quite what we're after. It's working backwards, just because that mute button is now, being controlled directly by that momentary button. On state of the momentary turns the mute button on. So there's a couple ways to fix that. We could just grab an inverter and put that in line after our momentary button, and then have the inverter, the output of the inverter, drive the mute button instead with a control signal. That would totally do the right thing. A really quick way to do this, to fix this right now though, is to just use the faders on the button module itself. Save you a step. We can easily flip the polarity of this by just changing these faders just like this. And now when the button is off, it's putting out 100%, which is muting our audio channel here. And if we push the physical button, on level is now 0%, and that pops the button out. So now we have audio passing. So it's now become a push to talk. Okay. Let's look at another way to deal with a mic. If it's not a push to talk you're doing, it's probably a mic toggle that you're looking to do. Probably two of the more commonly used ones. So let's look at how you'd pull that off. Let's go to our control modules again. Grab a momentary button again here. And this will be the same deal. I'm going to right-click this momentary button, set it up to remote control. Again, local analog input on the NX. And we'll choose our switch 1A. And hit OK. There's our switch 1A assigned. I'm going to hide that for now. And something we do need really quick is I want to we need to have an audio channel happen in here so we can have something to look at. So I'm going to just quickly throw on, we'll pretend that's your mic audio again, and I'm going to snag this meter again here, duplicate that. Now we've got, again, something just to monitor here. Okay, so what we want ultimately, again, we want to control the mute button of this, but we want it to act like a toggle. So they push the button, they tap the button, it toggles to mute, they tap it again, it unmutes, and so on. So how do we do that? We need something that's going to hold its state from this momentary pulse that we're giving from this momentary button, and that is best accomplished with a flip-flop module. So if we go down to our control logics here, under control modules again, control logics, here's our flip-flop, and we'll just simply wire this button into the trigger input of the flip-flop. So what I'm going to do is we're going to have this, well, let me do a quick push and just show you guys what this looks like, just at the bare bones before we go any further here. So we can just kind of see the action of the flip-flop. Pull up this guy. Now at this point, we haven't done anything. We haven't assigned control or anything like that. We're just going to look at only the button and the flip-flop. So I have the physical button in hand. Keep your eye on the Q and the not Q, basically. So we're going to flip. I'm going to push the button. It's going to flip over to Q. And keep in mind, this is a momentary button. So every time we pulse this flip-flop, it's just a single pulse. It's going to change its state, and it's going to hold that state, which is very useful because we can turn a momentary thing into kind of a latching thing. So every pulse flips it, and it holds that state. So that's perfect for driving the toggle, for that mute button on this gain block here. So what I'm going to do is, again, I'm going to assign a control signal to this mute button. I'm going to set up to remote control signal assignment, go down to select, and this time I'm going to choose 1129. That's the flip-flop, as you can see here. And we just kind of need to pick one. I'm going to go with the not Q. So whenever that not Q is high, logic high, our mute button will be on. So the channel will be muted. And because of that, because we're assigning to not Q, whenever Q goes hot, well, that means that not Q is low, and that means that the mute button will pop itself out and the channel will be unmuted. We'll see that in a second here. Let's give that a push now that we've done that. Make sure we got a control signal on there. We do. Okay, so right now you can see we're in the not Q state. Remember, this mute button is being driven by that not Q logic output right here. And so that makes sense. We are now muted. If I tap the button again, keep your eye on the flip-flop, it'll go to Q state, and that'll pop the mute button out. And so it's holding that state for us. Toggle it back to mute, and so on until the end of time. So let's take a look now. That handles the mute button toggle. That does not give a status indicator to anybody who's actually got the button in hand. Usually there'll be some LEDs on the mic or some indicator if the channel is open or not. So this is a great chance to use our logic outputs. We've talked about our logic inputs so far on this file, but we haven't done anything with our logic outputs. So let's start with that. LED control. So we obviously, when the channel is muted, we want the LED to go red. When it's unmuted, we want it to be green. And again, we know that our not Q, this is what's driving our mute button. So that's going to be our red state, our red LED. Whenever the not Q is high, we need that to drive our LED to red. So let's go ahead and grab, again, we're in control modules here. We'll go to control outputs this time. And you'll see local logic output 1, 2, 3, and 4. These actually represent the physical logic outputs in the back of the DSP. So these are tied to the physical world, these particular modules. I'm actually going to grab 2 of them. We're going to use logic output 1 in a moment. That's going to be for a green LED, a green state. We'll use logic output 2 for the red. So Here's our red state. Let's go ahead and wire in our green. This would be, by the way, if the LEDs they had, like the actual physical LEDs they had, were actually 2 discrete LEDs. If it's like that Shure one that we looked at earlier, you would just only need 1 of these local logic outputs, because that thing is already listening. It's already got its own logic. It's kind of listening, if you will, for 0 volt or 5 volts. In this case, we're going to pretend that there's 2 discrete LEDs, a red and a green. So let's give that a push and see what that looks like. Because there is one gotcha here that we got to look at. Pull up the logic output so we can see those. And here is our gain, and the flip-flop, and the button. Okay, there's all the things. Get that out of the way so you can see the flow. Okay, so right now you'll notice, let me just toggle it a couple times so we can kind of see what's going on. Right now we're in the unmuted state. The flip-flop is showing Q, which is what we want. And right now, logic output number 1 is on. And that means that's what we want. We want, you know, when it's unmuted, we want to drive that green LED. This is going to be our green on LED. However, remember that these are active low. So when the logic output has actually been activated, like it is right now, it's actually putting out 0 volts. It's not putting out 5 volts. So that means that if we're just driving an LED directly from this thing, it's not going to light up because it's putting out 0 volts. It's nothing. So what we want to do is we need to flip the polarity of our logic outputs to make it work. So it's, you know, when it's turned on, it is putting out the 5 volts to directly drive those LEDs. It's going to be the same for both on and off state. You know, it's the same concept regardless. If it's on, it's putting out 0 volts. The quickest way to do that is to just use these on and off threshold faders directly on the logic output module itself. If you just flip these numbers, 51 and 49 here. That is the quickest way to flip the polarity on these logic outputs for sure. Now that I've typed that in, you'll notice that let's flip it back to Q, to the unmuted state. Now our logic output number 1 is showing, you know, it's coming in 100%. It is being triggered. However, it's now active high. It's putting out 5 volts now that we've inverted it. And the same for our off state. This would actually light up the LED. You could use an inverter as well, but again, I like to do things the shortcut. You know, why add an extra module when you can just do it with the faders? Let's take a look at how to work with a pot in here. I do want to go over that. The potentiometer. Let's have a look at, I'm actually going to duplicate this via here. We'll use that over here for some audio. And I'm going to, as usual, grab a gain block, throw that in line. And again, a meter, just so we have something to look at. Okay. So what we want is to have, well, let's start with the very simplest thing, actually, before I get ahead of myself. Here's a fader with some audio coming through it, right? If we right-click this fader, set up to remote control, I have a potentiometer wired into external control input number 2, as we saw earlier. So if we go to the NX local analog input, we'll choose pot 2. Okay on that. Let me turn this on again so we can see what that looks like. Superimpose, and we can see that we've assigned pot 2 to this fader. Now, let's go online and see what that looks like. And you'll see that it actually just shot up to almost 12 dB. That's because this fader is now being controlled by an analog control in the real world. So it'll always follow where this potentiometer is at. So I'm turning it down, as you can see. And that is the most basic, simple volume control you can do. Simple 10K pot directly driving an audio fader and a gain block. The thing is that gets interesting is, what if you want to limit their range? Maybe you don't want them to be able to turn it all the way up and hit 12 dB, they'll blow the system up or something. Conversely, you don't want them to turn all the way down and just have like a bunch of dead space down here at the bottom of the pot. Maybe it just needs to be like minus 36 all the way up to like 0 dB or something like that as their range. There's a couple ways to do that. The way I like to do it is with a scalar module. But the thing is, to limit this, you don't want to directly drive this gain fader. At least that's not how I would do it. You can, let me show you another quick path since we're looking at it right here. If you want to directly drive this and give it a range, there's one way to do it directly, directly in the configure external control inputs area. We go to input 2, and we set the minimum level to say something like 20%. I'm just guessing at numbers here. Maybe we want their ceiling to be 80%. Now, if I turn the pot all the way down, it only goes to minus 30 dB. If I turn it all the way up, it goes to plus 1.3. Those are just the numbers I guessed at. So that is one way to limit them, is again to go into here and start playing around with the minimum and maximum levels in the calibration screen. I don't like to do it here though, because I don't know about you, but I don't want to memorize what percentage is 0 dB. I just took a stab and got somewhat close. It could be 78, but there's a way that I find much easier to do to help tune it, versus having to go in back and forth with that screen and then look at the gain fader. So if we go back in here, I'm first going to get rid of my control that I put on this pot right here, on this fader rather. So we're going to delete pot 2 from this fader. That's going to be in Remote Control Manager and Tools. All your analog controls are found in the Analog Control tab, right? So here's our gain fader that we just added. You can see again that it gives you sort of the module. Let's go ahead and delete this control that we were just looking at. So I was going to say that the module number is important here, so you know which one you're deleting. So just match that, basically gain 1132. We'll remove that, and now our pot assignment is gone, and we just have a standalone fader. So what we want to do is, again, I'm going to show you a different way to scale that range, give them a different range of control. So let's go into control modules as usual, control inputs, and here's our fader, the standard control fader. And we are going to right-click this fader now instead of the gain fader, and assign our pot to this guy instead. Set up to remote control, local analog input, pot 2. And there's our assignment there. And what we want to do is we want to scale it. We want to give them a low and a high, put a ceiling on them at the very least. So let's go under, I believe it's controlled processes. Yeah, we want to grab a scaler. So we'll just wire that guy directly off the fader. And now we want the output of this scaler. Let me pull up that GUI so we can see it. We want the output of this scaler to drive this fader. So how are we going to do that? With the control signal, of course. So let's right-click as usual. Right-click the fader, set up to remote control, do a control signal assignment, and I managed to hide the module we're trying to do. We're looking for scalar 1135 back here. Here's that. We're going to grab the control output from that scalar module. Hit OK, and now we have our control signal flag showing that this thing is being driven by something else in this file. So let me push that, and let's just see how you would work with that. So you can pretty much leave the input side. Well, let's start with this. As I move the pot, you can see that it's directly. Oh, you know what? I need to go back out and change the range of this pot. I forgot I left it at some weird value. Configure external control inputs. Let's reset that to 0 to 100%. That way we get our full range. And hide these flags. So now you can see that things are directly related, input to output. They match perfectly. So they still have full range. And there's a little bit of, oh, that time it went to 100%. You can see the pot is not quite getting there sometimes, all the way down and all the way up. We'll ignore that for now. So if you want to put a ceiling on them, the best way is just to turn the fader all the way up. Obviously have your system muted, your amps off if you're doing this. Turn the fader all the way up. Keep your eye on this gain fader up here. And I'm going to set the ceiling on this scaler by just moving this guy down. Now keep your eye on that fader. We can kind of just work it down until we get to, let's just say we want 0 dB as the ceiling. I'm going to say 86.1 or 85.8 maybe. We'll get real close. There we go. 85.9 will do it. And so now if I move the fader, I'm going to go all the way down with my pot, goes to 0. Totally off. There we go. Crank it all the way up. And now we're at, I guess I got my numbers wrong because my pot wasn't actually hitting 100% when I tuned this thing apparently. Oh, that time it did it. All right. So this pot needs to be calibrated, doesn't it? So that's how you'd set a scaler. You could do the same with the low, by the way, if you turn the fader all the way down. Keep your eye on that fader. And that's now as low as they can go. So there's their new range. That's what they get. I want to show you a couple of other things that are useful. Oftentimes people use linear faders or linear pots rather versus a log or audio taper. We have ways to deal with that if you want to change that taper to something else. I'm going to just cut this wire and pop this over here for now. Let's get it back to full range. So right now we've got a linear fader, linear pot rather. We want to convert it to audio taper. So what we can do is look at the control modules again, and I believe we're looking for control processes. We have these taper modules that will convert whatever to whatever. We got a linear coming in. Let's do a linear to audio taper and see what that does for us. We double click it. Let me actually wire this up here first. Okay, fader is off all the way down. We've got our linear to audio taper. As I turn it up, you can kind of start tracking. It'll actually track where we're at in the curve. So you can see that doing this, we're not getting a whole lot of action. Most of the range of the pot is wasted. I'm coming in I'm at 43% right now and just only putting out 3%, and we're at minus 69. So that's not a very good setting, I would say. But you can start kind of tweaking the ranges, tweak the curve here. If you want to go super extreme, this is absolutely horrible. But back it off here. As we turn it down, you can see we get, a way more aggressive at the low end of the pot. And as we turn up, so we start getting more of a reasonable curve here that's actually useful and gives them way more like full range of usefulness with the pot. So something to be aware of. We've got a couple different curve options in here. There's also actually a custom one, which is pretty cool. You tweak that one, you can actually go in and kind of draw your own madness if you want to. I wouldn't recommend that one, but let's see here. That's how you would change the taper. Something else that's really cool is when you're dealing with analog lines like this, sometimes pots are noisy in the sense that, maybe you'll see like the input percentage kind of like when you're live online. Let me just simulate this. Let me just push this file. There might be some noise coming into the analog input, basically, the external control input rather. You might see that as like a fader kind of bouncing around a tiny bit, which is not ideal. You might see something like this happening. You see how that percentage is just slightly changing. Probably not really audible or a big deal, but could potentially be annoying, at least for those obsessed with such things. But there's a way to kind of get rid of that noise, kind of a switch debounce, if you will. And we can do that with a ramp processor module. I wish I had a noisy pot that I could actually show you like what that looks like in reality. But if we go to the control processes and go to ramp processor, if we wire that in, give that a push. If you have I have actually a noisy pot at home. I have a monitor controller I built with a DSP, and the pot is a little bit noisy, or it's the ADC that's being a bit noisy or something, but it is creating little tiny like 0.1% jumps back and forth. So I used a ramp processor to iron that out. So you can see what this does is it just slows things down. Like if I was to increase this to some crazy level, you can see that I watch this as I turn the fader all the way up, and over 12.9 seconds, it's going to ramp it up. So it's a way to just slow things down. This is obviously an extreme example, extreme setting, but let's say we go to something like 0.1 up and down rate, which is, no one's probably really going to hear that lag. The way to debounce is the difference threshold. So if we set this to something like, 2% or 1% or something like that, nothing, if the pot is sitting there moving itself by like 0.1%, you'll notice that nothing's changing here on the output as I wiggle this just barely. You can see it changing, but since it never goes over that threshold of 1%, the output of this never changes. So that's how you like disregard any noise. It just never comes to the output of the output of the ramp processor. Sorry. So you could just have that in line and just feed your taper to your scaler in this case, and that analog noise will never reach your actual gain fader. Okay. And you can do that with a switch, by the way, too. If you want to debounce like an analog switch, you could actually stick a ramp processor in line here as well. And so, when you push the contacts, push the switch or release the switch, those contacts will kind of flop around really quickly, faster than you can hear or see, but without a scope or something. But this will disregard that so you don't get false triggers. So ramp processor can be used on a switch as well. We're just about done. If you guys have any questions, definitely chime in quick. This is one last thing I want to show you, and then we'll be done. Just a really quick thing with a kind of a sequence kind of thing. You could use another usage of logic outputs, basically. This is just kind of like it's just a sequencer, basically, is what this is, driven off of a latching button. What we've got is a chain of delay logics. For now, just kind of ignore this stuff down here. Let's just look at this first sequence up here. We push the button in, it's going to trigger a delay logic. And that delay logic is going to instantly trigger a flip-flop to hold a state. And what we're going to do is put a logic output on each one of these flip-flops. And by the way, I just tried to drag out local logic output number 1. I already used that in this design. So you can't reuse these modules over and over again because they are tied to the actual physical logic output. And you don't want 2 different logic circuits fighting over the same logic output. That's going to be a mess. So you're only allowed 1. So I'm going to go back out here and actually just delete these 2 that we used earlier. Let's just throw those in really quick. Actually, you know what? I'm not going to throw those in. Just pretend that they're there. Just because in the interest of time, I'll just do this one. 1, 2, 3, and 4. Those will be wired here, right? What we've got, though, is we push a button. We push this latching button. It's going to fire our delay logic. And it's going to fire our first logic output. It's going to hold for 2 seconds, and it's then going to fire, because we have our little chain right here, it's going to fire the next one in line. And that in turn is going to fire this flip-flop to fire local logic output number 2. Wait 2 seconds, fire the next one, and so on down the line. It's going to do 1, 2, 3, and 4 over a period of 8 seconds. I'm going to go ahead and just push this so we can see what that would look like. Bring up the control meter so we can see it. Let's see here. Let me pull up a few things so we can try to see the whole circuit here. You have enough real estate for all this. And I mean, why not? Let's get our flip-flops in there too, right? Okay. So I'm going to push the button, and keep your eye on the control meters over here. Pretend we're driving logic outputs, basically. I'm going to go ahead and push it, and 2 seconds goes by. Next one fires, next one fires, and the next one fires. So that's how you would build a quick, I guess, a power sequence, or a sequence of something. We could drive anything with this if you wanted to. LEDs, whatever. And as a bonus, we can reverse the sequence. That's what this bottom part is doing. When the button is popped out, you'll recognize the inverter from earlier. That's going to take our off level, which is 0%. So when the button is off, the inverter is going to fire that, change that to 100% and fire this second chain of delay logics, which is going to undo our flip-flops and put them back to not Q state. It's going to reset them all in reverse order. So you'll keep an eye on the meters over here and the flip-flops. I'm going to release the button, and there it goes. We're slowly undoing our sequence. So you could actually use that. That could be a scheduled power on, power off kind of thing. Actually, you could have 2 presets assigned to this button. Let's say preset 1, and then we have the off state, the power down sequence. Set that as preset 2, and then you could go into your event scheduler, and you could actually trigger that. Looks like I already did something in here. But you could add an event. Power on. That's preset 1. We fire that at 12 p.m. 7 days a week. And now that sequence will happen every day at 12 p.m. And we would add a second event to power down. Preset 2. Recurring 7 days a week. Now we've got our scheduled power on, power off. Okay. Let me see if there's any last minute questions here. Looks like we're good. So that's it for today. Again, this webinar was recorded and will be available to rewatch soon. If you want to get your hands on a completed site file, it should be available with that webinar once it's online. In the meantime, hit us up at support@symetrix.co if you have any questions. And thanks again, and signing off.